Yes, fine.
So the next part that I will discuss, there's mainly the analysis of what's called quantum mechanics from an axiomatic viewpoint, because those, from the limitation of those I consider both of them, Heisenberg and Bohm, founders of quantum mechanics, and the reason I would like to say the reason why, if you want, assuming that my tech works next Wednesday.
I think that would be very interesting. I also have a recommendation on a reference to the last paper that was published by de Broglie in 1965. It was published in French, but there is a more recent English translation. And I read that after our meeting last week, and I thought it would be very appropriate to bring up de Broglie's views as well, because he came before Bohm in terms of creating a hidden variable type of theory. Although what de Broglie was especially interested in is nonlinear extensions of the Schrödinger equation that give rise to solitons, and then he wanted he wanted to have a theory in which the soliton was controlled in the way that was predicted by Bohm through this guidance relationship between the wave function and the particle motion. So de Broglie really wanted both. He wanted both the wave function and the particle, and both of them to be described by a single nonlinear equation.
Yes, he was the discoverer of the soliton idea, but the study by Prince, the de Broglie was Professor de Broglie was a non-local theory, but he never published anything because he presented.
He did publish in the late 60s, in about 65.
Non-local, because he was attacked by Einstein followers.
Oh yes, definitely non-local. Yes.
It is non-local. Oh, in this case, I'm definitely I will be interested to look at.
Yeah. But what one means by non-local, I think you have to be very careful to define exactly what that means.
Many meanings.
So it may not be non-local in the sense in which you meant, Dr. Santilli.
I agree, because what we meant. The way we use the non-locality, the idea of non-locality, quantum mechanics is mainly an integral over volumes to emphasize that we are dealing with volume and not with points. And then over volume is then used to recover identically and uniquely quantum mechanics when the particles are detached and they are at the mutual distance more than 10 to minus 13 centimeters. So the volume integral becomes zero. Basically, the wave function multiplied by the summation conjugate and then the volume integral, the integral of that product. So when this over the entanglement, Einstein EPR entanglement is zero, then you recover quantum mechanics uniquely and unambiguously.
But the type of non-locality that was directly of concern to Einstein involved two particles widely separated that were entangled over distances that precluded explanation by relativity, by special relativity, so that the influence of one particle on another could not be described by a mechanism that was consistent with relativity.
Yeah, I don't understand why Dr. Santilli's theory eliminates that possibility.
Oh no, it certainly doesn't eliminate it. But in Einstein's view, in the original EPR papers, there was no concept of contact. There was no sense in which these particles were in contact with each other, because they were too widely separated to be described as being in contact by relativity.
That's particle would represent as being a point. the moment the particle is extended, the overlapping of the wave packet, if you call it overlapping of the wave packet or call it contact of wave packets, it's just a terminology. But the point is that those waves, they do overlap. And that's the what we call EPR, not quantum.
So if you have an electron located, say on Alpha Centauri, and you have an electron located on your desk here at Earth, these are separated by 4 light years distance, right? But the quantum theory says that if these 2 electrons were originally entangled and they did not interact with anything else during the time that they were separated, then if we measure one of these electrons, if we measure the electron on the desk, then we immediately have an effect on the electron in Alpha Centauri. And so
not necessarily effect, but you know what the outcome will be in Alpha Centauri, not necessarily a direct effect. Just
well, yeah, I mean, you know that if someone measured it on Alpha Centauri, you know what they would get.
Right? Yeah, that's true.
Right. So the point, but I think what Dr. Santilli was saying is that in spite of the fact that these electrons are separated by 4 light years, their wave functions still overlap in some sense.
Yes. Again, experimental evidence, as well as theoretical evidence, the wave packet of one electron becomes identically null only at infinity. Now, it is obvious that with our current method and equipment to detect, energy, we can approximate the electron again 10 to the minus 13 as this period of a wave packet within 10 to the minus 13. However, at Alpha Centauri, even though it's extremely weak, it does indeed, the wave packet does indeed exist. Those are the new conception of the universe as one single total integrated body. We're talking about the universe. Total integrated body of particles that are that of course, but you need a civilization 1 million years ahead to have equipment so sensitive to measure detect the wave packet of an electron in Alpha Centauri. But however, it exists, it is there. But this is also my point of my next lecture. All those studies, the fundamental notion that was, in my view, was missing. All those beautiful studies, I consider them the founders of Adorno-Descartes, Heisenberg, de Broglie. My God, those are my teachers. But they miss a central notion, namely that the interactions that, in my view, I beg you, the gentleman, the professor, in my view, that those in the non-linear, non-local interactions, they are not derived from a potential. They are not derived from a potential. That's the key issue. They're not potential. They don't admit potential. You cannot represent them with a potential. In that sense, so mathematically, you are not variational self-adjoint, are variational in non-self-adjoint. And physically, you cannot introduce a potential. Here is the potential, the partial derivative. I get non-linear theory. No, you cannot do that. It will not.
I think this would your comment would make me promise, perhaps in some coming months, to describe the theory that was presented by Bill Poirier, professor of quantum chemistry at Texas A&M. He published in 2007, I believe, a theory that was based on Bohm's notion of trajectories, but he showed how to get rid of the wave function altogether, and so that one could discuss the interaction between trajectories. And these are still trajectories of single point particles, but in Poirier's view, these particles occupy different worlds, and the interactions between the worlds is what gives rise to the quantum mechanical effects in Poirier's theory. So the cost of non-locality and non-linearity is to change your notion of physical space to include the possibility of many parallel physical spaces. At least that was his view. So, and I think that changes things radically, but it also is a difficult conceptual step to take. Right?
This theory produces number. They represent physical event, you know, made with experiments. You see, this is the same.
No, but this theory of Poirier's is described in terms of potentials. Like there is a potential for one world to interact with another world, but it's the nature of that potential is different than the potentials that are in classical physics. But still they are describable in a potential form.
Those are theory. Those are variational self-adjoint theory. This is again. The main structural novelty of hadronic mechanics is to admit that not all, some of those interactions, they are not derivable from a potential. So that this means you can represent them with anything except the Hamiltonian. The moment you see potential, you have a Hamiltonian. Now that's the long discussion with the Professor Eisen.
Yeah, so I think that we should hope sometime during the next few months to be able to get into the detailed discussion on these issues.
But it's best to discuss after my presentation, otherwise we just
certainly
time to have Professor Garret. So.
Yes, so I think we probably should move on to our main speaker as we originally agreed.
Oh, this is fine. I'm learning a lot from the conversation. But I'll talk a few things that might be related to these ideas too. So
great. Yeah, so Dr. Garret, Dr.
Okay.
Sobczyk, please continue.
Okay, so I'll share screen then.
Yes.
And I'll try to open up my first page here if I can. Okay, so this is just my
so far so far we don't see your shared screen.
Oh really? Why not? I can see
I don't know. I can still see you, but no shared screen.
Oh, okay, let me see again. I'll try. Oh, that's pretty strange. Let's see if
you click
oh, okay, I think I know what's wrong. I have to, okay, just a second, I'll fix it. I have to go to the other screen here. Okay, let's see here. Okay, now if I come this one in front, how about that?
No, we still see only you.
Okay, let's see here.
When you're clicking on the share screen, you'll get a choice of which screen.
Oh, okay, that's
choose,
what I'm
right?
missing, I guess. Okay,
Yeah.
I'll hit the shared screen again.
Yes,
oh,
and then
okay.
make sure you choose the small picture that includes the item that you're trying to share.
See. Let's see if I can.
Then do the share. Then do the share after that.
Okay, let's see it. Okay. Huh. Oh, okay.
Yes, there you go.
Okay, so well,
That's
this
perfect.
is just the first page here.
Yeah, it's not in large, like full screen mode, but can you make it larger?
Let's see. Let me see here. Okay.
It's okay for me.
Yeah, it's okay, but it's only partial screen. Like,
how's that?
Well, no problem.
Not full
better.
screen yet?
That's pretty close. That's good.
Okay, well, I'm not really spend much time on this. It's just basically what I want to talk about.
Great, yes.
Geometric, well, I've talked about geometric algebra G3 quite a bit already, so I won't spend any time on that, but basically I like to talk about the iso geometric algebra of Euclidean space. I think the concept of isogeometric algebra is important to better understand exactly how Dr. Santilli's theory differs, in what respect it's limited by the use of an isogeometric algebra, which maybe my understanding is not perfect. I'm sure it isn't perfect on that score either. So maybe that would help. Okay, so let me see if I can get to the next slide. Okay, I closed that, so I'll have to go to my share screen again. And let's see if I can get to the next one here. Okay, I don't really want this.
For the time being, we see only your picture.
Okay, so let's see if I can get on this share. Okay, let's see.
Yes, you're not currently
Okay.
sharing anymore.
All right, let's see if I can start sharing again.
That looks promising. Yes.
How about,
What
can you
was-
see
what-
this December 23,
No.
2021?
Yes. What we see is a list of files.
Okay, well, okay, I need to get,
There are 5 PDF files here. The one in the middle is isopoly.
okay, let's see. Oh, I see what you're seeing then.
Yes. Where your
Yeah,
cursor is moving now.
That's
what
the
we
one I
see.
want. That's the one I want to share.
So if you click on that, I presume it would open it. Maybe.
But maybe Professor Garret selected this window for share, but not.
Just the window instead of the screen.
Yes.
Yes. That's another thing that can make things complicated. Is that when you're sharing with Zoom, you can choose either to share your entire desktop. That means with all the different windows that you have open, or you can choose to share just one window alone. And so what I saw just recently was that you were sharing only the window that contained the list of files. So that, I think now you have to stop your share again and then go back to share either the entire desktop or just the window that is the one that contains your presentation.
All right, let's try again here. Okay. Okay, that's what I want to share. Okay, let's see if I can share that. How's that? What do you see now? Anything?
Yes.
Okay.
Now, yes, what I see is the first page of a PDF document, December 23rd, 2021.
Okay, that's what I want. That's what I wanted to share.
Yeah.
Okay.
That looks perfect.
Okay, so let's go ahead with that then. So again, the first thing again is just the standard basis of associative geometric algebra G3 of Euclidean space, consisting of these elements. Well, there's 8. The basis consists of 8 elements. A scalar 1, 3 unit vectors along XYZ axis, 3 bivectors, and then the unit pseudoscalar I equal to E1, 2, 3. And of course, the relationships they satisfy are, since they're unit vectors, Euclidean unit vectors, they have square plus 1. and they're anti-commutative, so nothing that I haven't talked about before. And bivectors, unit bivectors in Euclidean space have square minus 1, which is easily follows by commuting the E2 and E1. As does the unit bivector, also has square minus 1. It's easy to, using the anti-commutative relationships to prove associative. Okay, so this, I think, original in my part, namely how I write the what I call the spectral basis of this geometric algebra G3. Okay, now I'm getting it. Okay, so so when I write down U plus E1 U minus E1 U plus U minus, that means that these elements are exactly the basis elements. If you have a matrix A given down below A1, this basis corresponds just any element A corresponds to A11 U plus A12, the corresponding element of the basis then. So that's what we write on the next page here.
Can I ask just quickly about these annihilating idempotes?
Okay. Okay, they satisfy these relationships. U plus times U minus is equal to 0, which is very easy to compute since just multiply 1 plus E3 times 1 minus E3, you get 1 squared minus E3 squared, which of course is 0. That's why they're mutually annihilating. If you sum them together, U plus U minus, well, the E3s cancel out, you get 1. And if you multiply E3 times U plus, what happens? Well, you can see it just E3 times 1 is E3, and then E3 squared is 1. So that's why we say that E3 times U plus or minus is equal to plus or minus U plus or minus.
So could you choose like E2 instead of E3?
Yeah, you can multiply by anything. In fact, well,
so the choice of U is somewhat arbitrary.
Oh, well, that's right. You can generate idempotents with, but that's just the standard Pauli matrices are using that choice of E3.
I see.
And of course, that's the choice. That choice is due to the choice of E3 as being the spin axis.
The
so
Z axis, yeah.
So that's the whole reason why people use E3 as a spin axis. Well, here you have the matrices of E1, E2, and E3, which are just the usual Pauli matrices. So in other words, if you take U plus minus, or U plus minus U plus minus E minus, you get E3. Okay, so if you go back, you can maybe see that better. Okay, so you have a 1 here and a minus 1 here. So it's U plus minus U minus. And that just gives you E3, because remember the idempotents are plus or minus. So if you take U plus minus U minus, you get 1/2 E3 plus E3, which is just E3 then. Okay, do you understand that?
That's interesting, because the sigma 3 represents the spin 1/2. It's the fundamental point of Bell's inequality. And it's plus or minus depending whether the spin is up or down.
That's right. Yeah, E3 is the direction of spin.
It's the direction of the spin. Plus or minus 1 as an eigenvalue, but the spin operator is 1/2 the Pauli matrices.
Exactly.
By the J operator, which are 1/2 of the Pauli matrices. So that's why even though sigma 3 as an eigenvalue, plus or minus 1 at the spin level is plus or minus 1/2. When you go at the level of SU2 spin algebra, it becomes 1/2 spin.
That's right. We're just giving a geometric interpretation to the matrices. A matrix is just the coordinates of the particular element of the geometric algebra related by
And so,
this equation 1. And here's the coordinates of each element. Well, it's a complex matrix because remember, that's the pseudoscalar element, is a volume element, E1 times E2 times E3. So the reason why this matrix is complex is because, well, but the matrix only contains elements of the geometric algebra, namely
and this
scalars plus pseudoscalars.
This matrix, equation 1 there is a matrix of operators, right?
No, that's a matrix of, well, E1, E2, and E3 are unit vectors along the X, Y, Z axis, a geometric interpretation of these elements.
But U,
Yes, that's correct.
U plus is an operator, isn't it?
Well,
Like,
no, it's just the sum of scalar 1 plus or minus E3. So it's a
okay, then
plus,
maybe another way of saying it is that it's an element of the Clifford algebra and the multiplication.
That's
and the
right.
multiplication that we're talking about here is the Clifford multiplication.
That's right.
Okay.
And
All right.
So,
let me say that this is this is the most beautiful formulation of Pauli matrix and spin and half throughout my entire life. I want to say it explicitly. Congratulations. The moment I saw it, I became very excited. At the purely Pauli level, it's truly standard because there is lots of not only the geometric beauty, but also some very deep physical meaning.
well, that's right. It has it's completely, the elements of geometric algebra are just unit vectors along the X, Y, Z axis. Bivectors are bivectors in the XY plane, XZ plane, and YZ plane. And then the pseudoscalar is a unit trivector, E1 times E2 times E3. They all have geometric interpretations.
And I think
That's the way I'm
very
trying to
clear.
understand.
I think that's very clear. But when I was just sort of contrasting the matrix at the bottom of the page, where you have
Okay.
a matrix of scalars, right?
That's right. Those
And the
are
multiplication is no longer Clifford or
well, the matrices
whether it is
multiply in the usual way. That just
Mhm.
shows the isomorphism between the geometric algebra of vectors, bivectors, and pseudoscalars with the algebra of matrices, the coordinate matrices. Which,
well, in the last matrix, the multiplication would be complex multiplication, right?
Well, no.
Well, remember now, a pseudo I squared, I is the E1 times E times, that's the unit volume element. In the geometric algebra, it has square minus 1 by, if you multiply I times I, you have E1, E2 times E3, E1 times E2 times E3, and then you anti-commute, you know, to get to get rid of the vectors, you get E1 squared minus E1 squared minus E2 squared minus E3 squared. You know, it's all just algebra then.
So whenever I see a complex number, I should think in terms of that number as having a volume.
That's well, it has a scalar part, a real number part, and a pseudoscalar or volume part.
The real number part alone presumes that the volume is 0, right? But a general complex number would have a non-zero volume.
That's right. We're interpreting a complex number in this case just to be the sum of a real number plus a trivector, a unit trivector. Well,
yes. So
x plus iy.
So
but
all
I now.
So in the sense in which Dr. Santilli referred to iso numbers, we're already talking about iso numbers here in a sense, right?
Well, that's right. We're going to give them a geometric interpretation as iso.
Yes.
Well, we'll come to that. That's my next slide.
Okay, great. Yes.
Okay.
Because we have to verify the axiom that this interpretation of number, a new interpretation of number, has to verify the conventional axiom for a numeric field. That I have not done it. We will.
Well, but it follows immediately because of the way I've constructed this basis here. You see,
yes.
If you put it's very easy to prove the equivalence of the Pauli algebra with with the geometric numbers they represent. But I think of a matrix as just the coordinate matrices of a geometric number in G3 or the Pauli algebra.
Yes, I want to make a comment, but Dr. Page, your comment is rather deep, and I appreciated you made it, because you don't have an isotopy unless you have something that you start. Isotopy don't create theory; they just enlarge them. So therefore, to get the next formulation, which will be the iso-Pauli, the essentially defined on isonumber. This means that there has to be some structure of an isonumber in the conventional Pauli matrix. This is another aspect of the beauty of Professor Soczyk's formulation.
Well, I think, this has been around now. David Hestenes, of course, thought about it, 50 years ago, but the thing is, it's still not universally recognized for whatever the historic inertia of mathematics or whatever you want to call it. Still, well, I guess more and more people, the engineering community have picked it up. Computer vision, robotics, there are many applications like computer scientists are using of geometric algebra now. Okay, anyway, we can go to the iso-Pauli matrix algebra now so you can see exactly how it fits in. Okay. So of course, Hestenes was originally interested in the Pauli algebra because of its deep relationship to the Dirac algebra. I think it's extremely beautiful, this idea of Hestenes. I guess it was there was a close relationship that must have been recognized in Dirac algebra and Pauli algebra. Namely, you can consider the Pauli algebra to be the even subalgebra of the Dirac algebra, where in the Dirac algebra, a vector is represented by a bivector in the Dirac algebra, anti-commuting bivectors which have square one. A bivector can have either square plus one. A Euclidean bivector will always have square plus one, but you call it a space-time bivector can have either plus one squared or minus one squared, or you can have a nilpotent bivector, a bivector which has square zero. If the point lies on the light cone, then it'll have square zero.
Yes, I agree. Gamma matrices, but the very definition of gamma matrix, you need the Pauli. But as you indicated, that it's a subtraction, not, of course, not a one-to-one correspondence.
Okay, so
but I like the fact it's on that same point. I like the fact that you referred to the Pauli algebra as the Pauli algebra of the observer. I like that.
Okay.
Because the Dirac algebra has nothing to say about an observer as such, right? It's about space-time structure, but the Pauli algebra is exactly in the sense that you just mentioned, right? Requires that you define an observer, and then the Pauli algebra is in the space of that observer. Whereas, right?
Exactly.
This is Oshevich's views.
But let me also say that in the full geometric algebra, which we wrote down, the basis of a real number one, the 3 unit vectors, 3 bivectors, and the pseudoscalar is actually sufficient to talk about the observables for any observer in relative motion to each other or whatever. The Pauli algebra G3 is sufficient to talk about all the observables or each, which I'll again explain by that picture I showed you previously.
Yeah, that I didn't want to get directly into it, but that is in fact where perhaps Oshevich would differ from your statement, that one ends up with something a little different if you require it to be a relationship between observers. But
okay, let me just say that was the motivation for my paper with Professor Bayliss in Windsor, because he did not understand how he uses G3, the geometric algebra of Euclidean space, to do space-time to do relativity theory. He does not use the Dirac algebra, and that's And so you can say that this interpretation of the Pauli algebra is really equivalent to the way Dr. Bayliss has done his research in special relativity and electrodynamics. Is all in G3. So
let me make one clarification, if I may, regarding Professor Ruggero. Professor Page, what we have done so far, we are talking about one single observer, and everything is not only is it's called direct representation, namely representation in coordinates of the experimenter. Now, what Professor Ruggero discusses something extremely interesting, much more complicated when you have two observers. But this has nothing to do with our problem at this moment. So I will not enter in the discussion.
Yes, I see.
Keep going.
Yes.
okay, we can go ahead then with this equation 2. That's exactly what Dr. Santilli has referred to as a hidden variable in his theory or of quantum mechanics.
With one fundamental clarification that should be made, even perhaps in our final paper, we should clarify. Lambda is in reality the transformation is non-unitary, and it is a diagonal expression of lambda, and then the other one over lambda. But the fundamental notion that is not that transparent in our paper, but very transparent in every. You look at my paper in which I derived as ISO Pauli, Acta Applicanda Mathematica, 1998, is expressed very, very clear. Here is the point. Lambda is a function of the wave function. Lambda is an arbitrary parameter. The only thing has to be positive definite, but otherwise totally unrestricted. Functional dependence on wave function. You have the nonlinear theory by Heisenberg or a non-local theory by or whatever. So this is a very fundamental point. Now it is after having said so, at the same time, keep in mind, because we end up with a number. Keep in mind that once you know all the data of the wave function, basically that wave function can be reduced to a number. It is the case when you have, for instance, if you have a circular orbit. If you have a circular orbit, then the isodifferential calculus coincide with ordinary differential calculus, and therefore therefore you don't see the dependence on the psi, because psi becomes a number. But in general, at this stage, when you learn lambda is the bracket, wave function, integral wave function, non-locality, anything you want, sorry for the.
Well, that's fine. So again, that's the way I started out thinking about Dr. Santilli's material, is by writing lambda equal to e to a hyperbolic angle phi. Okay, so you have. That means you can write lambda as a sum of some hyperbolic angle phi plus sinh. Okay, but now look at how E3, in particular, I'd like to clarify exactly equations 2, 3, and 4, which you can see. So we write lambda as a sum, and that's the same thing as, okay, we can always do that because we know that lambda is positive definite or larger than or equal to 0. Of course, in this notation, phi would have to be equal to be 0. Let's see, phi would have to be what, large negative, right? Or yeah, a large negative number to approach 0. It's never really equal to 0, cosh plus sinh. But for large negative numbers, it becomes arbitrarily close to 0. Since cosh, okay. Okay, so now look at equation 3. Okay, if you take e to the power of phi times E3, for a real number phi times E3, you get cosh phi plus E3 sinh phi. So in other words, e to the phi 3 consists of a real number cosh phi plus a sinh phi times the vector E3, Okay, again, E3 is just the vector along the spin axis, which is the z-axis, I guess you call it. Okay, so remember now that U plus is that idempotent. So that just means that if you square U plus, you get U plus. Well, you can easily multiply 1 plus E3 times 1 plus E3 and see that times 1/2, you get U plus squared is equal to U plus. That's why it's called an idempotent. Okay, now the interesting thing is if you multiply e to the phi E3 times U plus, you get exactly e to the phi times U plus. Okay, because remember, if you multiply E3 times U plus, you get U plus. So essentially, the U plus absorbs the E3 and it just becomes, that relates then equations 2 and 3 then. Where, okay, so e to the phi is given by equation 2, and e to the phi E3 is given by equation 4. You can see the relationship then. Very simply remember that if you multiply E3 times U plus, you just get U plus, okay? It absorbs it. Okay, well, that's what I explained after equation 4. I'm just going through that calculation. So you can clearly see why it's the case then. Okay, well, also you can see why. Okay, that's the equation showing E3 times U plus is U plus, E3 times U minus is minus U minus. So that distinguishes U plus from E minus by what happens when you multiply by E3. Okay, let's go to the next page. Okay, now we come to my representing then an iso matrix. Well, this is the coordinate matrices of iso elements in the geometric algebra. Okay, so this is Santilli's equation number 36 in one of his papers that we have a copy of. Okay, so you have the matrix that he gives us are the matrix of sigma 1 hat is just equal to, as you can see, and if you take it back to the spectral basis, you can see why it works out that way. So these are the coordinate matrices of iso elements then in Dr. Santilli's iso polyalgebra.
May I make a comment, please, to clarify that?
Okay.
Understand I think the mathematics is extremely clear from your presentation, Dr. Garret. I would like to do my comment from a physical viewpoint. So when you look at those isopoly matrices, those are e to the minus p, you have to think about wave function. This is a strictly non-linear theory, as well as non-local if you want, or virtually any. But the nonlinearity is represented with the isotopic element. Without the isotopic element, it's impossible to, without the isomathematics, no possibility of formulating this. Another point, so think about the nonlinearity from a physical viewpoint. Whenever you see field, is wave function. Another point that I would like to, which is also clearly elaborated in this paper of 1998, I should say, I'm sorry. Is that the main idea that is eventually that we eventually brought to numerical value. The main idea expressed here is to add the degree of freedom, and here is the key point, to the conventional spin 1/2 without changing the value of the spin 1/2. Which because if you look at the paper, that paper in 1998, you see other realization of the realization of polymetrics that do not represent necessarily spin 1/2, but they represent the spin of the proton in the core of a star under monstrous pressure. We expect not to be 1/2, but that's a separate story. But back to what we are considering now in nuclear physics, no, the spin 1/2 has to be preserved. And so at the degree of freedom, and that's inspired by Bohm. That's Bohm was research for this hidden degree of freedom. But embed this degree of freedom in the notion of spin. This is the key aim.
Dr. Garret, your microphone is disabled and the share screen seems to have disappeared. Your microphone is still disabled. No, we still do not have any audio from you.
Look at the bottom left bar and see if there is a slash over the audio. If it is a slash,
Okay.
There you go.
Okay, yeah, I have to hold my space key down now to do that. Let's see if I can get that.
Yeah, on your shared screen, we need to see that again.
Okay, let's see if I can get back here. Okay, can you see it now?
It's right now it's blank, but there may be just a time lag.
Okay.
Yes.
we got it.
Now we can see it.
Okay, well,
Could I know this is going rather slowly, but I think there's some important points here, and I'd like to back up just to the previous page for a minute. Yes, so, okay, so on this page, so far we have only discussed the equation. Equation 3 is interesting because the exponential in equation 3 is clearly an exponential in the Clifford algebra, correct?
that's right. Remember, E3 squared is equal to 1.
Yes.
So
this is peculiar
to
the
odd terms that give rise to sinh phi then.
But equation 2 is ordinary classical algebra, a complex algebra
exactly.
of real numbers,
yeah,
right?
Exactly.
Yeah. So the okay.
And equation 4 relates the two.
Yes. Now on the next page, when you went to 5, equation 5. Now these coordinate matrices are, like, should I interpret these as being matrices in sort of the matrix algebra of complex numbers, or should I?
Sure, complex numbers, because they're the E3 or the pseudoscalar E1 times E2 times E3 is in the center of the Clifford algebra or the geometric.
Yes.
So it behaves exactly like a complex number.
If I may say so, the interpretation must be the same as done with Pauli matrices. Otherwise, there are inconsistencies. Whatever we do with the Pauli, we have to do with isopoly. That's the idea of isotopy. If we exit from this rule, we are talking about something else.
But the beauty, everything in the geometric algebra has a geometric interpretation, but it behaves exactly as complex numbers.
That's the beauty of it.
So your equation 6 then is expressing, say, sigma 1, for example, is being expressed.
That's right. That's in.
But these multiplications here in equation 6 are in the geometric algebra.
Yeah, G3.
Necessarily.
They're all elements of G3 still. We're still in the geometric algebra of G3.
So there's an implicit isotopy here, right? That's, I mean, maybe it's not so implicit. It's actually
we're interpreting. We're giving a different interpretation to the complex matrices.
Yeah, so that the sigma hat that you write there alone without the square bracket around it is
it has its coordinate matrices given in 5.
Yes, and And
So
yet
that's-
it maps directly to 5, right? Back to 5.
Yes.
But we
But
sort of,
remember, if you look at, if I go back a few pages here, you go back to the spectral basis idea. This thing, you see? So
Yes.
again, that's the position of the A11 component, A12 component, A21 and A22.
clearly,
So remember,
it's clearly a matrix
there's the
in,
coordinate matrices,
it's-
you see? That,
Yep.
so A, and then each of these A11 corresponds to
but
this
what,
element,
whereas,
A12 corresponds to this one, A2, that's the components then, for these
I just
bases.
want to be clear in my mind, so that your item number 1 is a matrix of Clifford elements, whereas the matrix at the bottom of the page is a matrix of complex numbers.
Well, they
and
behave
you're-
like complex numbers, but they're still.
Well,
can
but the
say they're complex
isopity,
numbers.
the one is the isotope of the other, I guess, is what I'm trying to say. Right?
Well,
Well,
it's just giving the elements of the geometric algebra a different interpretation. We're calling sigma 1 now to be equal to, as you see it in the screen, isotopic sigma 1 is this element, but it's constructed from the same elements in G3. It's just a different combination of the elements. It gives a different geometric interpretation to the elements of G3. But the interesting thing is it behaves just like a Clifford algebra. Under the isotopic product,
Mhm.
you can see
Yes.
here, sigma 3 squared is equal to the isotopic unit squared, and so on. You know, that's the interesting thing of, so this is defining the elements of the isotopic geometric algebra. Notice the unit is extremely interesting. In equation 7, 1/2, that's now our new unit in the isotopic unit, is exactly e to the phi E3.
So the advantage here is that you can express the isotopy, you can express that as an expression in Clifford algebra.
That's right. It's just an
So
element
it's not something that you
G3.
sort of have to pull out of a hat. It's something that is built into the Clifford algebra to be able to represent that
That's right.
the isotope is an element still within the algebra. It's like,
Yeah,
I
everything
suppose,
is in G3.
so in contrast with what Dr. Santilli said in a couple of lectures ago, he said you often choose the unit of the isopity outside of the original algebra.
outside your ring.
Yeah, but here it's an element within the ring defined by Clifford algebra.
Basically, I need your attention for a moment, but there is a basic point that's to be clarified here. The point that this we added, is if you look at section 2 of our paper, at the bottom of section 2, the point is clarified. This algebra is a conventional Clifford geometric algebra. Only the elements are generalized, but the algebra is not an iso-Clifford algebra. No, the reason, for several reasons. First of all, because the product is the conventional one, it's the same product as for
Yes.
not only that, but also for other reasons that so that from a physical viewpoint, if you do an isotopy of the Clifford algebra, we get off track. Basically, why? Because then you have to introduce another hidden variable, which is redundant, and then becomes a problem what you do with that, how you represent it, and so on. Whenever you think of this, think of conventional associative product for which the multiplicative unit is 1. Now, when you go to this ISO unit, we clarify in the paper that this is the unit of the ISO Pauli matrix, and it is not the ISO unit. You can introduce an ISO unit if and only if you have an isotopic product. The product is conventional. So there is potential misleading and misleading point here that as Professor Garret correctly formulated this unit of the matrices. They're perfectly okay. A theory may have several, especially since you have many long bases on many things. You can have several units with, provided you define properly. I believe the units properly identify as not being the an ISO unit of the entire algebra because the entire algebra is not an isotopic, the product being conventional.
No, the ISO unit is defined, the ISO product is defined in terms of elements in the geometric algebra.
Yes.
Namely, I define that, let's see where I define that. Well, here, for example.
But then you have to insert the inverse of the ISO unit in between every product. You get
Oh, that's right, that's right. That's the way it's defined. Let's see if do I have a.
And you lose.
All right, here it is. So, okay, the definition of an ISO A, if you have any element A in G3, okay, so A is an element of G3, then the corresponding element in the isogeometric algebra is A hat. And you get that simply by multiplying A times the unit ISO unit.
Unit of the iso-Pauli, not the unit of the entire algebra.
But that's the iso-Pauli algebra. That's 1 hat. So those are elements in the iso-Pauli algebra.
Yeah.
So A hat, iso A hat. So given any element A in G3, the corresponding element in the isogeometric algebra is A hat. And you simply use the product that we defined in G3, you multiply A times what the unit iso element is, and that's what I defined up here.
But you can say that in a different way. You can say that you have made, if at this point you make the transition from the Clifford algebra,
right here,
the iso-Pauli matrix. If you go to the spin algebra, the Lie algebra, SU2, and yes, then you can do that at the level of the spin algebra because the iso-Pauli can only be derived within an iso SU2 Lie algebra. So, but you have to exit from the Clifford algebra, which of course you can. It's perfectly admissible, and only there's a question to be careful about the moment you see you have an iso product. Absolutely, you can. Then you must have an iso unit.
No, what I actually think is on the level of the Lie algebra, the Lie algebra of the iso-Pauli algebra is exactly identical to the Lie algebra of the Pauli of the iso algebra.
The structure constant, but not the product. The product is isotopic. It's the hat sigma 1 star product, the hat sigma 2 minus hat sigma 2 star. And so yes, this turns out to be the structure constant are the same, or you characterize the spin 1/2. So what you state is correct, Dr. Garret, but you at this level, if you're the real iso unit with the corresponding iso product, you are at the level of the SO2 Lie Santilli iso algebra that produce those iso-Pauli. Then you need, and when you pass at that different algebraic level of Lie, then you need necessarily an product, otherwise you will never reach the iso-Pauli. But sometimes there's possibility that this may be confused, that this iso unit may be confused as the iso unit of the Clifford algebra. No, it is not, in my view.
Okay, well, I try to be a little more explicit. Again, I'm defining everything in terms of the usual geometric algebra G3, which is isomorphic to the algebra of Pauli matrices. For example, addition in the iso algebra is exactly equivalent to addition in the geometric algebra. But look at number 12. It's only the multiplication that has to be defined differently. But I'm defining the multiplication in terms the geometric algebra G3. So in other words, if you have any two elements, A and B in G3, but remember, you define the multiplication of A times B as A times T. Maybe I should have though I should have A hat
I
times
think
B hat.
that's no. I think that yeah. Yes, you should. Yes,
I should
it
have A hat times
should be
B
A hat, T hat, B
Star.
hat. Yeah.
Yeah, it should be A hat star B hat. Oh, okay. Here you see the definition of A hat. Okay, A hat
Yes.
is equal to A times e to the VE3, and B hat the same thing. So this should be a hat here. It's a mistake.
Yes.
I need
On
A
both.
hat star B hat, and then
Yes, and on the
here is
next
correct.
one. Is correct? No.
But equation 10 is correct for me as well.
Oh yeah, no. The second one is correct. Yes.
Yeah, that's
Yes,
right.
because T hat plays two roles, right? It's both.
So the isomorphisms, so they cancel each other, is perfectly correct.
Yeah. But I think would it be accurate to say that in your case the isomorphism that we're talking about is an endomorphism, like we're taking Clifford algebra and mapping it back into itself.
Exactly.
Yes.
Exactly correct.
Not an isomorphism. No, it's an endomorphism.
Endomorphism. That's right.
Yes, endomorphism, but it's a one-to-one endomorphism, right?
Exactly. It's just like, yeah, it's like the isomorphism between the algebra of Pauli matrices and the geometric algebra. That's an isomorphism.
Yeah.
But you can consider that to be an endomorphic. Well, no, that's mixing.
So in that
operators
sense, in the sense that Dr. Santilli said above or before, that we're not introducing an iso-Clifford algebra. This is just Clifford algebra.
Otherwise, we cannot derive the number. We cannot derive
They are.
No, that's, yeah, so let's see. So let's look at the end between 10 and 12. So it should be I think it should be A hat times B hat. But then this equation, okay, then I'm replacing T hat by what it represents G3. So this side of the equation is in the usual geometric algebra, and this is the definition in terms of the iso algebra. So it should be
A definition.
T hat, and you can see you're still left with A times T hat in between, so you get this then. That's what it represents.
on the right, equation 10, that's correct, absolutely, yes.
But T hat is, you have to be careful about the notation, right? Because T hat, you defined above, like a few.
I guess it is confusing, actually.
At the top, you should write out exactly what T hat, how T hat is defined.
Yeah, this is abbreviated.
But equation 5, I think, or 6 maybe.
Yeah, maybe I should have another line in here or something on the side of the iso.
Well, in fact, there's this between T hat and the item in the center of the last equality, right? Those are according to the definition of T hat.
No, I guess this is all elements. No, it should be A, B, and G3. Okay, so here I say for A, B, and G3. Okay, they're isomorphic as endomorphism. You can think of the isogeometric algebra. So this is in G3. And again, the definition of the stars, you have to sandwich in the T hat there, A times. So this is all in G3 actually, except for the star. The star operator is defined again in G3. And you've changed the geometric product. So it's A T hat times B. So everything is in G3 here, defined in G3.
This will characterize a hat G3.
That's right. I'm defining everything in terms of G3. So I'm defining that operation of iso multiplication as an operation in G3. just the ordinary geometric algebra. So,
It's an endomorphism, yes.
that's right. So if I wanted to multiply A hat times B hat, then I would have to substitute. I would have to replace A by A times the unit isotopic unit. So then we get a different equation here. We'd have well, this would be the same, except at the end we'd have a E3 or E to the phi times the unit. I'm sorry, it's a little confusing.
But wouldn't those cancel? They cancel if you do
Well,
that.
at the end I would get, let's see, maybe I have the next page here. Okay, here, this is important. Oh,
Yes.
okay, here you go.
Yeah,
That's what I
there
wanted
you're,
to tell you.
that's what you're saying.
Yeah.
Yes,
So
getting
A
ahead
hat
of
times
yourself.
B hat. Yeah. Okay, now you can see how it works.
Yeah, they cancel in the end, right? So
Okay, so in the end, you can see you get here the isotopic unit at the end then.
Can you go back, please, to the preceding equation? Here, you see here, you use the product not of A hat and B hat. Those are all not
Exactly. Yeah, that's right. Those are elements. They're just A, B, and G3, as you can see here. I'm correct here.
isomorphism here, but not an isomorphism. As Dr. Page correctly said, then when you go to the next equation, please, can you go to the next equation?
yeah, it's at the bottom there.
13.
So now is the equation defined with the elements, with the hat on the top of
Yeah, that's right. But here, actually, we are showing that G3 is isomorphic to the Clifford algebra G, the iso-Clifford algebra G3.
yes. Yes, that is the importance of what you are doing. In other words, you are not introducing a new, introducing a new input variable, but you use the same input variable, and so and you show that the isomorphism, which is parallel to the isomorphism of the Pauli versus.
Yeah, exactly.
Beautiful, it's beautiful.
So I do think that geometric algebra clarifies these ideas of what is an isotopic Clifford algebra. In fact, there is a paper that we give as a reference that people have explored it somewhat.
Still, they do a full-fledged iso-Clifford geometric algebra with very intriguing application to the Bohr theory that you may like the applications to Bohr theory. I don't, but they use my here, but they are always enough to quote my work but I was the first to prove that by using the isotopy can provide what I can define a strict confinement of quarks, confined with an identically null probability tunnel effect. So very, very trivially, you get the Hilbert space inside the hadron coherent with the Hilbert space outside, and so therefore there is no possibility of transition. Oh, but this was my work. I did it many, many years ago, just to show the possibility for Bohr theory. That's the side part.
Okay, so equation 14 is really expressing the relationship between the okay, yeah, so again, the first, I'm defining the geometric product in the isotopic algebra. Okay, this is the geometric product in the isotopic algebra. So what I mean by that is you're using the star operation, but in terms of the elements of the ordinary geometric algebra, it's just A times B times E to the E3. So that proves the isometry between the iso-Clifford algebra G3 and the geometric algebra. They're isomorphic algebras really, but everything is given a different isotopic interpretation. Like the unit is equal to that 1 hat, which is E to the phi E3, 14, you see. So all we're doing is replacing the geometric product with the geometric product times the iso unit. That's the only difference then. So I hope that clarifies the geometric interpretation of Dr. Santilli's isogeometric algebra. It's not really all that different from ordinary geometric algebra. Namely, the ISO unit is different.
Your point, the unit.
But as Dr. Santilli said, the ISO unit contains a non-zero volume.
That's right. It's cosh, a scalar, cosh phi plus E3 times sinh phi. And the, well, times.
Not necessarily. See, Dr. Finch, this is another point that allow me.
It's a vector, not a pseudoscalar. It's not a volume element.
No. There's a point to clarify that this was from your comment which of course you made a comment, of course, in good faith, but which I need to clarify. In this paper, in which we're talking about this novel non-linear degrees of freedom of the notion of the conventional notion of spin, the idea of the volume exists nowhere. Why? Now, in the introduction, I do present, I made some considerable emphasis for the volume, but that is necessary. The volume of proton and neutron, which is experimentally measured, you cannot deny, because we have many enemies in particle physics. Not me, not Ruggero, will be your friends forever, but you'll make many enemies against you. But CERN, they will attack you, which of course in a decent, in a civilized way. But the point is this: that then that notion of physical volume plus the density was necessary for the first derivation. My first derivation of the magnetic moment, according to the Fermi-Weisskopf hypothesis. Namely the one which I published in Russia at the ICTP, at the Joint Institute in Dublin, 1994. That was a mathematical realization of their idea of Fermi-Weisskopf, and I showed that indeed allows that there you need actually the volume. But here, no, here we're talking about rotating the abstract notion of spin 1/2. And we're talking about the hidden degrees of that allows the exact representation of the exact same number. In other words, the physical number represented in this paper is identical to the number represented in my paper on 1994. To show that the nature is polyhedric, there are many ways in which you can treat the same physical reality. The physical reality, there is some kind of a deformation of a proton or a neutron, some change. That may be the word deformation that can be epistemologically wrong. There is a change, an unknown change in the transition from a condition in vacuum to one they are a member of the deuteron. And this change is polyhedric. You mentioned, Dr. Page, you mentioned the Gaussian, change the Gaussian. Yes, I said yes. It sounds very intriguing. And first I wanted to honor my mentor, my teacher, Enrico Fermi, was his idea, and I never met him, of course, but he has been my teacher in nuclear physics. I want to honor his idea, and that's what I did. There I needed the volume. But here, no, there is no volume whatsoever in this notion. I just want to clarify.
But what wasn't we went back to talking about the imaginary unit as a volume, right? Like E1, E2, E3 in Clifford algebra represents a volume.
It's a matrix, and so therefore, being a matrix can represent a volume. Yes, I think so.
Well, it's a volume in a geometric sense, right? In the sense of G3.
Absolutely, yes.
I'd like to point out the equation 15 here. You can see that the structure of the ISO basis is exactly the same as a structure of the spinor basis for geometric algebra. All you do is multiply it times e to the ISO unit, but everything else is the same.
I also agree, yes.
So that's why I would like to better understand exactly what the ISO unit means in your theory, Dr. Santilli. Can you say anything more about the ISO unit from equation 15.
First of the isotopic element. Maybe I can try to elaborate in my next lectures. Why? What is this? Inverse?
Could we skip back to an early part of this paper? Maybe equation 4, the first page, I believe. Did I? Yeah.
that?
Oh, yes. Okay. Now if you go to the next page, then you define T, right? T hat. Yes, here.
Yes.
Yeah, that's
So
the
okay,
inverse
so
of the
so what you
element.
just said here was that there is no pseudoscalar of G3 involved here.
That's right. It's a vector, the spin axis acts as a spin, and a scalar.
So there is nothing in geometric, nothing in G3 that we can associate geometrically as a volume with.
As a unit, or better, the isotopic element.
But the E3.
Oh, by the way, here, look at equation number 9. Look at equation number 9.
Yes. Mm-hmm.
That gives you the iso pseudoscalar in terms of an iso volume element and an iso bivector, which is interesting, I think. I'd like to better understand that.
Fundamental equation that allow the derivation of numbers, because you factorize the hat sigma 3 into sigma 3 multiplied by your quantity. That's allowed. That's the paper, the paper. So Professor Cruz, you were about to say something. Apologize. We are all excited about this. I apologize.
No. I wanted to say about the interpretation of the pseudo scalar in the before equations, but I think that it is there because how do you define E3?
E3, of course, in geometric algebra is just the z-axis, it's the spinner axis.
It's one of the basis elements.
Yes, but this base element is related with the product of E1 and E2. That's right?
Yeah, that's right. E1 times E2 is equal to I
Then
3. Well, I is, again, the trivector.
Then, yes. Then we have here one the representation of one object different of E1 and E2.
That's right.
That's right.
So for the isogeometric, as interpreted in the geometric algebra G3, the iso pseudoscalar consists of a volume element times cosh phi times a bivector, namely that's the spinner plane. E1 times E2 is the plane of the spin. Namely, that's E3 is perpendicular to E1 times E2. E1 times E2 is a bivector of the XY plane.
That's right. It's a bivector. Then and then I think that the iso that the definition of T have implicit this pseudo scalar.
Yeah, so
Exactly.
so you mean to write the expression for T not in terms of E3 but in terms of E1, E2, and the pseudoscalar?
No, not necessarily. Only
No, T is defined in equation 7. So
Yes,
that doesn't have any pseudoscalar in it.
It doesn't, but it could, right?
Well,
Because you define E3 in terms of the pseudoscalar and E1 and E2.
well, E1 times E2 is equal to I times E3, but E3 is just a unit vector along the x-axis, or the Z
Well,
axis.
see, instead of defining the spin in terms of an axis, define it in terms of the plane.
Well, that's
Yeah.
right. Well, that's just
Yeah.
the relationship.
Rotations occur in a plane, right? Rotations don't occur around an axis. They occur in a plane.
Well, the plane
It's
is
only in
each
three-dimensional space
Exactly.
that there's an isomorphism between these
Exactly.
two concepts,
That's right.
right?
Yeah,
One is an axial vector versus.
Well, that's right. That's usually the usual Gibbs Heaviside product. A cross B is equal to I times E3, or I times A wedge B. No, A wedge B is equal to I times A cross B. Well, I could write that down. So if you have two vectors, A cross A wedge B, that's the bivector of the plane of A and B, is equal to the pseudoscalar I times A cross B, well, that's the usual cross product vector analysis.
But if you just go up to your previous page and you had that definition, like it's fundamental to Clifford algebra, right? That
Yes,
a little bit further up.
Previous page.
One more page.
Do I have that relation? I don't know.
Yes,
Okay,
here.
here it is.
Yeah, E1 times E2. Yeah, well, E1 times E2 is equal to I times E3. That's easy to show that.
Yeah, I guess you didn't write it out explicitly, but it's
No, I didn't. That's right.
yeah.
But again,
still,
I squared is equal to -1, but it has a interpretation of a unit volume element of space. Well, it's a directed volume element of three-dimensional space.
so there is an implicit volume in your definition of T.
Well,
Because it's
that's
inherited
right. Well,
from
of
the
course you can
Clifford
write,
structure.
but also E1 times E2 is equal to I times E3. E2 times E3 is equal to I times E1. And there's three relationships there, not just
Yes.
yeah.
But your choice of E3 is just a convention. Right?
Well, that's right, to agree with the polyalgebra.
So but you could use the exactly equivalent convention would be to use the plane E1, E2.
Oh yeah,
right?
sure. You
To
can
use
define,
the bivector E1, 2.
Yeah, in fact, when I started, I was always thinking about E1 times E2 as, well, that's right. I didn't have the polyalgebra. I had something isomorphic to the polyalgebra, but physicists always use E3 or I times E3.
But really, they should be more careful and use the bivector in relation to.
Well, that's right.
But
Of course, there's three. Go ahead.
The difference is important when you get to the Dirac algebra, right? Because then you have 4 basis elements, and when you talk about rotations are still rotations in the plane. But spin in the Dirac algebra is something a bit more complicated.
Yes.
Well, again, as far as the Dirac algebra, we identify the polyalgebra as the even subalgebra of the Dirac algebra. But maybe I should go on to my next.
The important part is that means for a given observer, right? So you've sort of.
But any observer corresponds to a different way of cutting up of how you interpret vectors. Let me go on. Let me get that other
No,
picture
I understand that. Yeah, that's exactly.
Okay.
But that's exactly correct. That a given, what you mean by an observer is a particular way of factoring.
Of cutting up the Dirac algebra.
Yes. But in order to have this idea that spin can be represented in 3 dimensions, right? You need to first of all define an observer.
Well, that's right. The observer
and then
of
so it's spin. It's the spin that observer would measure, right? It's a different observer would measure a different spin.
That's right. That's right, because he picks a different unit vector. Well, no, you actually can pick any vector, unit vector to define the spin axis. But of course, when you're still in only one reference frame. So you have E1 times E2 times E3.
But you see, ideally, you want to be able to define what you mean by spin at Dirac's level, right? So you want to be able to define what you mean by spin without reference to any observer.
Oh, that's right. So
then spin becomes a trivector in G4. Yeah, I know that's a bit of a leap, but this is something called Pauli Lublansky. The view that spin is related to a trivector in the Dirac algebra.
That's possible, but again, that's the thing. You are very flexible in what you can interpret as a bivector or vector, depending upon the observer. It's the observer which defines what's an electric field and what's the magnetic field. It's only with respect to that observer.
So the problem that happens, I think, gets people very confused is to keep thinking of spin as if it is clearly defined in 3 dimensions. Like in which case the only thing you can do in 3 dimensions that's related to spin is a rotation around the axis E3. But that really, strictly speaking, is still a rotation. It's not spin, right? It's only what an observer measures of spin, right? So what's really spin, the intrinsic spin, is a pseudoscalar in the Dirac algebra.
Oh, yeah, that is correct. Indeed, the correct formulation requires necessary. I agree that it requires necessarily relativistic aspect. Also for another reason, you see it. It's my view that the theory, one of the many conditions for a theory that can be mathematically magnificent, but physical is a different issue. There are conditions. One of the many conditions that exist for a theory to have a physically, really deep physical value is the invariant over time. In other words, for instance, we have obtained, let me show the limit, the lack of completeness of our own paper. We have achieved a numerical representation of the hidden variable lambda representing nuclear magnetic moment. Strictly speaking, this is not enough, because then we have to prove that value is relevant to something is indeed invariant over time. The number is the same under the same conditions, but at different time, namely invariance, and that our group did achieve it, but we spent decades of work in constructing the isotopy of all space-time symmetry. So I didn't want to mention it because I entered too many reference too many things. But the point being, I agree with your point, Dr. Page. In order to prove the invariance, the transition from 3-dimension to 4-dimension is inevitable. It's necessary, and in this case, you have to add the density. Not only if you work with shape, you have to work. That's my paper in 1994. In this case, which is at the full relativistic level, and I proved the invariance over time by using the isotopy of the spinorial formulation of the Poincare symmetry. That's you need for spin 1 up. But in addition to volume, you have to add the density. Necessarily, you have to add the density. That's why the 3-dimensional matrix becomes 4-dimensional. That's Dirac. That's Dirac. Not at least in.
It sounds like a good subject for the next paper in your joint series of papers between Dr. Santilli and Dr. Sobczyk, and tackle the Dirac algebra next.
Okay. Well, I'd like to just, but related to what you're just saying, look at equation number 8 here. It's a very interesting equation because it's relating Okay, so it's relating with the iso vector sigma hat 1 to the geometric algebra vector E1 times the unit iso unit. So notice that sigma 1 hat is equal to E1 times the unit, sigma 2 hat is equal to E2 times the unit, and E3 is also, it's a definition of a passive Lorentz transformation. So you could interpret this as representing the iso unit vector sigma 1 as a passive Lorentz transformation of the rest frame of E1, E2, and E3 by multiplying it by T hat. I think this is new for Dr. Santilli's theory, although we'd have to, and I guess it's related to the Dirac algebra, which we could maybe talk about next time or sometime in the future.
That's we should look at the spinorial covering of the Poincare symmetry, which is the generator of the gamma matrices, and there you see all those virtually all of this feature. You do the symmetry, and you can see a fully relativistic extension of this beautiful expression here. That is the most fundamental one. If I may, I take a moment of your time. I would like to consult with Professor Cruz. Professor Cruz, I have a question. And also Professor Page, Professor Garret, can you, Professor Garret, could you teach me how to pronounce your last name, please?
Sobczyk.
I will apologize for my Professor Cruz. There are a number, and again, Professor Page and also Professor Sobczyk, there are a number of unsolved fundamental problems in isomathematics that in the event a solution is identified, then the physical implications are substantial. Let me flash you one. The isomathematics transform nonlinear equation on an ordinary space over a field into an isolinear, identical. It's the same, the equation is identical, but it's transformed into a form which is isolinear, namely verifies the axiom of linearity on an isospace, here again, if and only if expressed over an isofield. The fundamental problem open is the following, is a question. Now, since we have reached an isolinear, we reconstructed a linearity in an isospace, then an iso solution of the iso equation is very easy to locate. So, but the question is this isolinear iso solution also a solution of the original nonlinear equation? Because if the answer is yes, this is big for physics, because the solution of nonlinear equations not only gravitation and quantum field theory, etc., etc. So if you are interested, I can try to formulate a little bit more accurately some of those problems, and then pass it to you, and you can keep them in your inventory, and maybe someday, one day, if you're not interested, any of you, some graduates don't see.
The subject sounds very intriguing, but surely it's a large claim to say that any nonlinearity can be made linear by this isopity. Surely the range of possible linearities that can be removed, nonlinearities that can be made linear, must be restricted in some way.
Generally is unique. There is a theorem, this is in my book, Elements of Hadronic Mechanics. There is a theorem indicating that any nonlinear, ordinary or partial differential equation can always be identically written in an isolinear form. Generally, when you put identically, then the isotopic element is, if I remember well, this many years ago, is unique. So, but in any case, it exists. So isotopy turns non-linearity into isolinearity, which is linearity on isospace. This is what I wanted to write down for you.
Like, yeah, I think that would be very interesting because at least potentially it would have huge applications in the theory of nonlinear differential equations, of course.
Right.
And for example, even in computer algebra systems, the tools that we have for solving linear differential equations are much more powerful than the tools we have for the nonlinear case. So if there's a way to map a nonlinear differential equation into a linear system, even if it's in a different algebra, like it has to be in the iso algebra, then symbolically at least the computer algebra should be able to solve that using the algorithms from linear differential equations, and then presumably map it back into a nonlinear solution. But that would definitely be a revolutionary possibility.
Well, to make the transition from linearity to isolinearity, we know that. You embed all the nonlinear terms in the isoionic. That's basically the idea is elementary. I would like to clarify that this does not necessarily mean we got all the solutions of an ordinary nonlinear equation. No, my dream was that at least we found a method for a quick solution, at least a method for the quick identification of at least one solution of an nonlinear equation. How? By locating, by identifying the solution of the isolinear equation, and then projecting that solution in the original space and see whether that projection in the original space is also a solution of the original. So again, you have a nonlinear equation, you transform it into an isolinear form, you locate easily a solution. Then you have to map everything back to the original space over the original field, and then verify that indeed that is the projection gives you one solution of the original nonlinear equation. That will be big enough. That will be big enough. It will be very easy. It will be bigger, wider.
So did you say that you already have a paper that outlines this procedure?
Transforming a nonlinear equation into an isolinear one. Yes, this is a rather both at the algebraic as well as at differential level. The differential level a little bit more complicated, but still there. What we do not know is whether the solution, again, what we don't know is whether the solution of the isolinear equation, when projected in the original space, it gives you at least a quick solution of the original nonlinear equation. That's what we do not know.
It sounds like the kind of exercise that one could do using a computer algebra system quite easily.
Well, if you want, again, my proposal was just if you want to write it down as a problem, as an open problem, not as for that requires, that if you are interested, we will. And there are other similar problems that the implications are substantial.
Well, I would definitely be interested in any background papers that you have on this, specifically on this transformation that you were just mentioning.
Elements of hadronic mechanics that I have to dig it out. Honestly,
Sure.
not worked at this problem for over 30 years, 40 years.
No problem. And also, I would be very interested to receive a copy of this paper, Dr. Sobczyk. That this is a 5-page paper that you were looking at earlier.
I can send that.
Yeah, I don't think that was not the paper that you and or Dr. Santilli distributed a few weeks ago, right?
No, it was work I was doing for my contribution.
Mm-hmm.
But again, can you see the screen I'm sharing right now?
Yes, Ken.
Okay, so that's the figure that shows that each inertial system or each observer has his own interpretation of elements in the Dirac algebra, you see. Well, but it all takes place in G3, you see. This is the Euclidean plane of one observer, and the blue one is the Euclidean plane of another observer, and phi represents the velocity between the two observers. So as you go to the light cone, but they're all observable. The only difference between observer in the yellow plane and in the blue plane is they're moving at a different velocity. They're moving at relative velocities.
Yes, they're beautiful, very nice, very, very nice.
So this is what I like to, this is what Bill explored in our paper, while relating his way of looking at relativity in space-time algebra, the Dirac algebra, how it's related to this picture here. But it's all, it can be done in what, and that's the idea of a Lorentz, a passive and an active Lorentz transformation ideas too. Anyway, I wanted to show that.
When I look at that picture, I would like to relate it back to Olszewicz's notion of sort of splitting, of splitting the Dirac algebra into a time-like part and a space-like part.
Right. I would
and this is the space-like split for a given observer. And what you're calling phi is a component of the time-like vector associated with the observer.
Exactly. So
yeah, it's the same thing, I believe.
Yeah, so that's what we were thinking about. That, you know, Dr. Olszewicz wanted to use 3 to define. You know, there's a third vector that we were talking about that.
Yes, related to phi, right?
For the center of mass.
Exactly.
Center of mass of 2 observer, so that because that's the external will be the external observer that will be in inertial condition.
But I think it's in Olszewicz's case, we can get into this, but the thing is that the time-like vector associated with an observer is not a relative vector. It's an absolute vector in the Dirac algebra. Right?
Well, that's right. It's a unit. Yeah, we can go into that.
So,
it's a unit vector.
So it's
a Dirac,
yes, it's a unit vector, exactly. And so it's incorrect in relativity to refer to that time-like vector as if it's a velocity. It's not a velocity.
No, remember,
it's a property associated with the observer in an absolute sense. It's not relative to anything, right? So all velocities should be considered to be relative velocities, but yet there is a time-like vector associated with the observer. But that's not the velocity of the observer. The velocity of an observer is only relative to another observer, a second observer.
I think the best way to think about it is thinking about an electromagnetic field. If you take a unit charge and you move it, then the observer that's standing still will see an electric and a magnetic field. But it's all in the same Pauli algebra. You know, you have 2 observers, they're in space-time, but one sees an electric field and the other sees electric and a magnetic field. So
but to make all this work out, to make this all work out, you need a third frame, right? The frame in which you described the Dirac algebra in the first place, right? And that's in Olszewicz's case, that's what
algebra.
Well,
every inertial system corresponds to a unit time-like vector in the Dirac algebra. And it's a space-time splitting, what Hesny's called a space-time splitting. Namely, you take a position vector times a unit vector, you split it into CT, the time, and the bivector is in this, like E1. So E1, E2, E3 can be factored into bivectors in the underlying Dirac algebra. So anyway.
Yes, it's relevant for sure.
And before
I would like to understand in terms of Olszewicz's way of thinking about it, as you say, as a third vector somehow involved. I'm still
No,
not clear exactly.
Not a third vector, but a third frame.
Yeah, okay. So yeah, what is that frame? What is that third frame that you need to define two other frames?
Well, Shevich says that if you confine yourself to being in classical relativity, then the third frame is ether, basically. It's some global preferred frame in which you define everything else. But having
I'm
required,
wondering whether that third frame is necessary.
well,
time
that's the whole
rack
point.
vector.
Well, the reason the Oshevich claimed that it was necessary, if you insist on classical relativity, it's necessary because the composition of velocities is not associative.
Yeah,
Ultimately,
this is still different.
like that causes you enormous problems, right? When you cannot compose velocities in an associative way, then things get very confusing. So then his main point was to redefine what was meant by relative velocity as a binary thing, as being something that did not require the third frame.
But this is strange to me because the Dirac algebra, okay, has signature 1, 3, and the even subalgebra has signature plus, 3. I can't understand, and they are associative algebras. I cannot understand where the non-associative comes in. Where does the non-associativity come in? I never understood that point.
Well, I'm unfortunately we don't have the author who could stand up and give you like a 10-minute sort of presentation on the subject. But I think over time we might be able to continue this subject between you and I for sure.
Okay.
And I know Dr. Cruz also was like intimately related to the this research. So we could, at some point, we could return to this discussion of relativity, especially in relationship to spin in the context of this current paper. I think that would be very interesting.
Professor Sobczyk, I hope not to damage your name. Please, I formally invite you to publish the presentation of today in algebra group and geometry. Of course, it's an invitation at no cost and no limitation on length. But I think you're the good company because not Clifford Algebra, but there have been very, very few papers published in Clifford Algebra, but there are many papers connected to similar issue. So please consider my invitation. Okay.
Okay. Yeah. Maybe. Thank you very much. I'll certainly think about how to do that, and maybe some of it, like this figure here, I think is very important and related to this discussion too, of course.
Oh, yes, of course. Yeah.
Okay, well, I think we've exhausted our time limit today again. So I think we had a very interesting discussion. The only question I have, I guess, is next week. Do we have a particular proposal to continue in some manner for next week?
I'd like to remember a proposal. I would like to make it to review my correspondence with Heisenberg on axiomatic aspect of nonlinear theory. As the first part.
So would you be able to have that ready by next Wednesday, Dr. Santilli?
If Professor Cox send us the text, the tech shop link to the tech shop so that we can replace. If my tech shop works in a day or two, I think I can do it. Yes.
Okay, that would be great. If you could let me know if you were sort of prepared. I mean, this is an informal seminar, so we don't have to be rigorous and complete, but at least you have to feel comfortable enough to to make at least some 20 or 30 minutes of discussion.
This is my problem. And so, but I will, of course, I have to reinstall the tech shop. It will work. It will take a couple of days. And after that, I would like to also look at the axiomatic structure of some how can I say, the in-depth look at the physical consistency of this nonlinear theory by Bohm, the non-local theory by the Vichy, and so on, because those were the origin of, and then maybe open discussions. Yes.
Okay. Maybe along that line too, I would like to distribute to the links to the paper by De Broglie that I mentioned at the start of our meeting.
Send me the link. Yeah. We'll be very appreciated.
Yeah. Okay.
Also,
right.
Very interesting. I saw that we have Clifford for algebra. You look for our joint paper with Professor Sobczyk. At the end, there is the link to this paper by two Brazilian mathematicians on the isotopies of Clifford algebra and very intriguing application, very intriguing. All conventional, all standard application so orthodox application in which the isotopy are applied to make happy orthodox physicists. Okay, not me. No. Very well. It was very nice meeting indeed.
Okay, so we say goodbye for today, and we'll continue next week, hopefully with Dr. Santilli giving the main presentation.
Well, thank you very much. Have a beautiful weekend.
Okay. Thank you.
Okay, yeah, thank you. It's
Bye for
nice
now.
seeing you all again.